Hey, not today. Today we're doing a regular lecture. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good to hear. All right, so today I just have a standard lecture for you guys today. So we're going to go over frame equations, and so that's kind of the last of our unit here on direct stiffness. And so what you'll see soon is that frame elements combine truss elements and beam elements together. Okay. So we'll have a couple lectures of this. We're going to cover this on today and next Tuesday, and then we're going to start jumping into the MATLAB implementation. So we're going to start programming in MATLAB very soon. So the plan for the next couple weeks. So I expect us to cover frame equations today and Tuesday. Next Thursday, I want to do a review of MATLAB stuff, and so a review / crash course in MATLAB in terms of what you need to know. And then we'll spend the next week after that doing the MATLAB implementation. So for those of you curious about ANSYS, I do have one more ANSYS activity planned for the class. It's probably going to be after the MATLAB stuff, so probably closer to spring break. Just because there's a lot we need to go through from. Okay. All right, so on Tuesday, remember we had our first ANSYS activity. Hopefully you guys enjoyed that. At the end of that activity, there are more beam and frame problems, so make sure you take care of that. The due date for activity 1, both the ANSYS part and the problem set at the end is going to be next Sunday. So make sure you guys are on top of it. Okay. All right. Are there any questions I can answer before we get started for today? Okay. All right, so let's go ahead and get started. So the topic for today is frame equations or frame elements. All right. So like I mentioned before, frame elements are kind of the end goal for our direct stiffness unit here. And so up to this point, we've covered let's summarize all the elements that we've covered so far. So we've covered springs, we've covered trusses. Okay. So springs and trusses are quite similar in the fact that they both deform in the same way. So springs and trusses both are axially deforming members. And what I mean by that is that your element usually looks something like this. It's some slender element. Axial deformation is expansion or tension and compression. Okay, so the deformation is in the same direction as the element itself. Okay. All right, well, we just finished with beams. So beams have different deformation modes than springs and trusses. So beams have transverse deformation, and rotation. Okay. And so if we draw the beam element here, right? Transverse deformation is any deformation mode that's perpendicular to the main axis of the element itself. And rotation is a change in orientation or a change in slope of the element. Okay. All right. So, I think some of you have kind of pointed this out already. Some of you have already noticed this, but in reality, if you were to have just a rod just by itself, right? We would actually expect the deformation to be all three of these things combined, right? Not just limited to just axial deformation, not just limited to transverse deformation or rotation. Okay. And so let's say that you wanted to use direct stiffness to model a structure, right? So let's say that you have a bridge, you have maybe like a chassis for a car or something like that, and you want to model it using direct stiffness elements, right? I think you'd be kind of hard pressed to kind of choose which type of element that you would want. right? You could make the argument that they could be all truss elements. You could make the argument that they're beam elements, depending on the geometry, depending on the loading. But in reality, the deformation that you expect is probably going to be quite complex, right? And so it would make sense for us to have an element that kind of captures all three modes of deformation: axial deformation, transverse deformation, and rotation. Okay. We expect that when we use a software like ANSYS too, right? So we expect that whatever we simulate in ANSYS, it's going to capture all the modes of deformation. It's not just going to limit it to certain modes. Okay. And so of course, that we would have to kind of reframe our formulation. We'd have to develop a new element stiffness matrix. Okay. But the good news is that this does exist. Okay. And of course, that's the title of the lecture for today, which is frame elements. Okay.
Sure.
Yes.
So that means we can use frame elements to solve all the other methods?
Yep, you could. Yep. Normally, so frame elements, you'll see it's the most flexible in that it can capture all the deformations in every direction. But they can be a little bit difficult to use because you'll see their element stiffness matrix is 6x6, and they're going to be it's probably going to honestly take me 15 minutes just to write down the entire thing. So it becomes a question of convenience. And so but that kind of leads into our MATLAB stuff, which is once we learn the MATLAB stuff, it makes these things a lot easier to do. Yeah, but in theory, you can use frame elements for everything. Mhm. Okay, so that's the direction that we're going to go in for this week. And so because these problems get a little bit lengthy in terms of the writing, I only have a couple of examples. That's honestly the most that we can do in the time frame allowed. But this is mostly just to kind of motivate the MATLAB stuff. All right. Any questions on this so far? Okay. All right. So we're going to proceed in the same way that we did for the trusses and the beams. And so we're going to start with the element stiffness matrix. Okay. All right. So there are a couple of things that we have to kind of cover first. Just because the beam stuff we actually kind of left off a little bit in kind of a weird place too. So before we get to the frames, right? The element stiffness matrix I'm going to give you for frames is kind of arbitrary for any dimension, right? So if you remember from trusses, we went through that whole derivation of 2D trusses, and it involves sines and cosines and things like that. So before we get to the frame stuff, let's first talk about the beam element stiffness matrix. So before we present the frame element stiffness matrix, let's generalize the beam stiffness matrix to 2D. Okay. And so when you first read that statement, it might seem a little strange, right? Because the beam is kind of inherently kind of a 2D element, right? Because you have your beam going one direction, and your deformation is perpendicular to this, right? And so just naturally, it looks like it's already a 2D situation. But if we were to have a beam element that's angled, right? So if we have a beam element that's kind of angled up with the horizontal like that, right? Our deformation needs to be able to accommodate for that as well, right? And so we can kind of apply the same kind of transformation matrix that we did before to this system. Okay. Okay. The interesting thing about this, though, is that unlike the truss element, the beam element involves rotations, right? And the interesting thing about rotations is that they basically have the same, because they're unitless, right? The way that we measure rotations are without units. Okay. Since they're unitless, then no matter how we rotate our coordinate system, the rotations are always going to be the same. So we actually don't need to apply a transformation to the rotations. Okay. And so let me go ahead and show you. Okay. So on the one hand, remember the way that we did this for the beams is that, or for the trusses, is that on the one side, we have our deformation modes in the stationary coordinates. Or sorry, in the local coordinates. Okay. So these are beam deformations. In the local coordinate system. Okay. So those are on the that's in the coordinate system that's attached to the beam that's rotating with the beam. Okay. But then in order to use this, we have to transform this into kind of the fixed or the reference coordinate system. Okay. And so that reference coordinate system is d1x, d1y, theta1, d2x, d2y, theta2. Okay. These are the beam. Okay. So those are the beam deformations in kind of standard X, standard Y directions. And we have to add the thetas in there as well. Okay. Of course, to relate these two things, you need a transformation matrix. And so our transformation matrix is going to look something like this. Okay. It is a 4x6 matrix in this case. All right, so just for the sake of time, I'm just going to give you the transformation matrix, but the idea is the same. Okay. The idea is the same as our truss one. So right here is our transformation matrix. Okay. So you can see here I'm using S and C. So S and C are referred to sine and cosine, right? So if our beam is angled at an amount theta, S is equal to sine of that angle, and C is equal to cosine of that angle. Okay. So you can see from the matrix here that we're incorporating that rotation directly into our formulation. Okay. And this one right here, okay. That one right there is for the rotations, right? So remember, the rotations don't need to be transformed. They don't need to be multiplied by sine or cosine of the angle. So we can just kind of translate that over. Okay. Okay. So since this is the transformation matrix, I'll call it just T. All right, question. So doesn't this multiplication give us a non 4x4 matrix? So this isn't the element stiffness matrix. This is just the transformation matrix itself. So it's you can augment this. And so if you want to have this be a square matrix, you can augment this. And so instead of d1y hat, you have d1x hat, d1y hat, d2y hat, but then you just have a row of all zeros basically. So just like we did with the truss. So I think in the truss, I think we fully augmented it to be a square matrix, a 6x6, or in the truss, it was in the truss matrix, it was 4x4 since we didn't have the rotations. But for this one, I'm just kind of omitting that augmented row. Yeah. Mhm. Right. Okay. So now that we have this transformation matrix, we can pre-multiply it and post-multiply it by the beam element stiffness matrix. Okay. So remember, we did the same process for the trusses, and so we took our transformation matrix. Our transformation matrix is T underscore. Okay, we're going to pre-multiply by it, so we're going to have T underscore transpose multiplied by K. Okay, so this K right here is our beam element stiffness matrix that we used previously last week. So this is the standard one. Okay, the one that we have been using basically. Okay, and we're going to post multiply this by the transformation matrix again. Okay, and then what we end up with is something that looks like the following. So this is going to be quite a doozy. So we'll see. Okay, so the result, we still have our factor of EI over L cubed in front. So that's still a scalar factor out there. Okay? But everything in the middle here is going to change quite a bit. And it's not pretty. Okay. All right, so what we have here is a 6x6 matrix. And so we start out on the first row, 12s squared minus 12sc minus 6 times L times S. Okay. All right, remember S and C refer to sine and cosine. L is the length of the element. Okay. Minus 12s squared, 12sc minus 6ls. Okay. All right, so that's just the first row in the matrix. Okay. I'm going to cheat a little bit here. And so since I know that this matrix is symmetric, I'm not going to write out everything, every entry. But remember, whenever you write a row in a matrix, you just write it down into the same column, right? So we're going to use that same paradigm here. So now we're going to go on to the second row. And for the second row, I'm going to start in the second column. So that's going to be 12 c squared, 6lc, 12sc, minus 12c squared, 6lc. Okay. Third row is going to be 4l squared, 6lc, minus 12sc, 6ls. Okay. Each row becomes easier because we're leveraging the symmetry. Then we have 12s squared. Minus 12sc, 6ls. Sorry, I think I messed up the third row. Apologies. Let me highlight these. And so Messed up this one. All three of these, actually. I don't know where I was going. Sorry about that. Okay, so that row is 4L squared, 6LS minus 6LC, and then 2L squared. Sorry about that, everybody. I'm just double checking else. Even just copying it down from one sheet of paper to the next is a challenge. And then the next row, 12S squared minus 12SC, 6LS. Yeah, okay. Yeah, sorry about that. Yeah, so the third row, make sure you correct those three entries that I've circled in green. Okay, so the second to last row, we have a 12C squared minus 6LC. Okay. And then our bottommost entry here is going to be 4L squared. And everything that we don't list here is just symmetric. Okay. Right. So that's just for one element. So for one beam, that's just arbitrarily angled. So I will say that I this is kind of the point where 541 kind of separates itself from 410. So for 410, that's my undergraduate finite element course. I do everything up to beams, but I don't do frames with the undergraduates just because it gets a little bit extreme. But you guys are grad students, you guys can handle this. So we're gonna go through this stuff. But what you'll see is that I'm bringing up this frame stuff, and I have a couple problems like this on the homework. But this is not something that's regularly expected because this by itself is 36 things that you have to compute, and you're going to see the frames once we get to the frames, it's even more on steroids. And so, this is kind of more set up for the MATLAB stuff because this normally is a little bit too extreme for a person to compute.
Can you remind us what LS and C stand for?
L is the length of the element, S is sine of the angle, and C is cosine of the angle. So if you have a beam that looks like this, L is the length here, and it's angled with respect to the horizontal like that. So S is sine of this angle, and C is cosine.
You have to memorize it or?
No, absolutely. So I'll tell you right now. So we're gonna have a midterm exam on all the direct stiffness stuff. I'm not gonna give you a frame problem. I'm not going to give you a 2D beam problem because even just writing this down is just ridiculous to do. So, this is more kind of set up for the MATLAB stuff. So if all the first midterm stuff we've kind of already finished, and so the first midterm stuff is going to be like springs and trusses in 2D, and then beams in 1D. So this year we're kind of moving on to the next step. Yeah, absolutely. No. You can tell even I don't have this memorized. And the frame one I certainly don't have memorized at all. That one's crazy. All right, any questions on this? Okay. All right, so let me go ahead and delete this here. Okay. So that's the element stiffness matrix for a 2D beam. Okay. And of course, all that is built up for the frame. Okay. Okay, so I'm gonna present the frame to you in two different ways. And so I'm gonna give you kind of the standard frame element, which is just the 1D frame. And so the frame that's kind of angled kind of horizontally like this. Okay. And then I'll give you kind of the transformed version of an arbitrary frame that's kind of upwards like that. Okay. With an angle. Okay, so let's start with the standard frame. All right. So what's interesting about the frame is that it's literally just kind of it's kind of like an augmentation of a truss and a beam just kind of put together, right? And basically what we're assuming is that there's no cross interaction. So basically what we're going to see here for the element stiffness matrix is that you just take the truss elements, you take the beam elements, and you just smash them all together into one matrix. All right. So let's take a look at this. And so this is the standard one. So this is just F1x hat, F1y hat, M1 hat, F2x hat, F2y hat, M2 hat. All right. Let me label all the symbols here just because there's going to be a lot going on. So, for a frame element here, right? We have its length L. We have its cross-sectional area A. So A is going to be the cross-sectional area of the frame element itself. We have the E, which is the Young's modulus. So the Young's modulus is an expression of how strong the material is that comprises the frame element. And then we have I, which is its moment of inertia of the cross-section. Okay. So we have four properties to worry about here. Okay. All right, so let's start writing the matrix here. So first, in the top left here, we have AE over L. Right? That's a familiar face, and so that's what we had for the trusses. Okay. Okay. Next two entries are 0, so that's nice. Okay. Then we have a minus AE over L. Okay. Then we have two more zeros. Okay. All right. So I'm leaving myself a lot of room because the beam stuff is going to take up a bit of space. But remember, this matrix is symmetric, and so I'm only going to write in just the relevant rows here. Okay. Okay, second row. So we're going to start with the second column. So this is going to be 12 times EI over L cubed. Okay. So you can see here, this is kind of the beam part of the frame. So we have the moment of inertia being factored in, as well as the Young's modulus and the length. Okay. Next, we have 6 EI over L squared. Okay. Then we have 0. Zeros are nice. Then we have minus 12 EI over L cubed. Okay. And then a 6 EI over L squared. Okay. All right, third row. So third row here with 4 EI over L squared. Okay. Then we have a 0. I have a minus 6 EI over L squared. And then we have 2 EI over L. Okay. Next row is easy. Fourth row is just going to have an AE over L and then 2 zeros. Okay. Second to last row here, we have a 12 EI over L cubed. And a -6 EI over L squared. Okay. And then in the final bottom right entry, we have a 4 EI over L. And of course, this is still symmetric. All right. And so this is, of course, multiplying the nodal deformations here. So we have a D1x hat, D1y hat, theta 1 hat, D2x hat, D2y hat, theta 2 hat. Okay. All right. So we have a mess already, and we haven't even thrown in any rotation yet. And so, so the next step is going to be to transform this using our rotation angles. So we're going to factor in sines and cosines in here, and then that's when things get messy, because now the beam and the truss parts are going to mix together. And I probably won't even be able to fit it all in one screen, so we have to kind of zoom out and do it. But we'll do that in a second. I'll let people kind of catch up here. So are there any questions on this here? Okay. All right, so that's our standard frame element. So when rotated, and so in order to kind of generalize this to any kind of 2D orientation of the frame, we need to apply our transformation matrix. And just like we did with the truss, just like we did with the beam, we're going to pre-multiply this transformation matrix and post-multiply it as well. All right. So the transformation matrix for a frame looks slightly different. It's a 6x6 matrix. So it's a little bit different than the beam, but I think in the interest of time, I think we'll just kind of skip right to the element stiffness matrix. And so I feel like I've been hyping this up for 35 minutes now, and so this thing has to deliver now. So let's just do it. Let's just get started. Okay. So our element stiffness matrix. So I'm going to factor out an E over L. Okay, so that's going to help us out a little bit, just save us a bit of writing. Okay. And then we're going to have one massive thing. All right, so I'm going to write this in the same style as the previous two matrices, and so I'm going to rely on the symmetry here. So I'm just going to write in kind of the top right section of the matrix. Okay. But same as before, so we have our standard properties here. So E, Young's modulus, I, moment of inertia, length L, cross-sectional area A. Okay. We're gonna have S. S is gonna make an appearance. S is sine of the angle theta. C is cosine of the angle theta that the element makes with the horizontal. Okay. So just remember all that, because all of these are gonna make an appearance here. Okay. So our first entry here in the top left, we have A, the cross-sectional area, multiplied by C squared plus 12I over L squared S squared. Okay. All right, second entry. We have A minus 12i over L squared times sine and cosine, CS. Okay. Next entry here, we have a minus 6i over L times S. Maybe write that S. That S looks like a 5. Okay. All right, next entry here, we have a minus, parentheses, a c squared plus 12i over L squared sine squared. Okay. I'm scrolling already. It's not fitting on the same line. Okay. Next, we have a minus a minus 12i divided by L squared times cosine and sine. Okay. And then we have a minus 6i over L times sine. Okay. All right, so that's the first row of the matrix. Okay. I'll have to write smaller for the next rows. Okay, next row in the matrix. We're going to start with the second column. So first row is the worst. That's the one. That's the only one. Well, that's the only one we have to write every single entry. Next one is going to be one less. Okay, second row. We have a times s squared plus 12 I over L squared cosine squared. Okay. Next entry is 6i over L times cosine. Next, we have a minus a minus 12i over L squared cosine sine. Okay. And we have a minus a s squared plus 12i over L squared cosine squared. Then last entry here is always the easiest. You have a positive 6i over L times cosine. All right, third row in the matrix. Third row thankfully gives us a little bit of a break. This is the theta row. So this is the row that corresponds to the rotational degree of freedom. Okay. So this right here is 4i. Then we have 6i divided by L times sine of the angle. Then we have minus minus 6i over L times cosine. Last entry is 2 times I. Okay. All right, fourth row with a times cosine squared plus 12i over L squared times sine squared. Okay. Then we have next we have a minus 12i over L squared cosine times sine. Okay. Last entry is 6i over L times sine. 2 more rows. Okay. We have AS squared plus 12i over L squared cosine squared. Minus 6i over L times cosine. And the last entry, miraculously fitting it all on one page, is 4i. I know you guys probably don't care, but my writing has improved since the past 2 years since I taught this class, because last time I taught this, I could not fit it all on one page. I had to like zoom out and zoom in, and it was a terrible experience for everyone involved. So gotten a little better this time. I was able to fit it all. All right. So that's our element stiffness matrix for the frame in the most arbitrary sense possible. So this is as bad as it gets. This is the worst type of element out there. Right? So obviously, we'll do a couple of examples where these calculations are easy. As you can imagine, these calculations simplify quite a bit when your angle is either 0 degrees, either some function of 0 and 0, 180, or 90 degrees or 270, right? Because in those cases, either sine or cosine is going to be equal to 0. So that's going to cancel out a lot of these terms. But if you're doing it for an arbitrary case, so let's say if your angle is like 30 degrees, you're just suffering. This is just a terrible experience. So the ones that I'll give you for these ones are always going to be, either 0 degrees, 45 degrees, 90, something like that. If you're going to do this with any other angle, it's hard, obviously. All right, any questions on this so far? Okay. All right, so that's all the new stuff. And so, from here on out, we're just applying our same methodology. So let's just jump into an example. Okay, so for this example, let's consider a square or a rectangular structure. So we have a rectangular structure comprised of frame elements. Okay. So it looks just like this. Okay. For each bar right there is a frame element. Okay. We have element A, element B, element C. Okay. So we're going to say the height of the structure is 10 feet. The width of the structure is also 10 feet, so it actually is a square structure. Okay. We have a couple loads being applied here. So we have a load of 10,000 pounds being applied directly on this node here. Okay. And we have a counterclockwise moment of 5,000 pound-inches being applied on node 2. Okay. And actually, let me label the nodes. So we have node 1 is attached to the ground. Node 2 is right here. Node 3 and node 4. Okay. All right. We also need the material properties of each of these elements. Okay. So let's say that we have a Young's modulus of 30 times 10 to the 6 psi, cross-sectional area of 10-inch square. Okay. So these two properties are going to be applied to all three elements. Okay. We have a cross-sectional moment of inertia of 200 inches to the fourth. Okay. So this first moment of inertia I1, this is going to be applied to elements A and C. Okay. And then we have another moment of inertia I2. This is going to be equal to 100 inch to the fourth. Okay. And this is going to be applied to element B. All right. So nodes 1 and 4, we're going to assume are fixed to the ground. Okay. So since 1 and 4 are fixed to the ground, the only nodes that are going to that are going to deform here are nodes 2 and 3. So we want to compute. We're going to compute the deformations of nodes 2 and 3, and we're going to do it via the direct stiffness method. Okay. All right, so we have a fairly simple structure here. So we have 3 elements arranged in a square. We have all the properties given. So this is just kind of our standard direct stiffness problem, and so there's not much else to say than just to start writing it through. So the good thing about this structure here is that everything here is either horizontal or vertical, and so that's going to help us out when forming our element stiffness matrix. Okay. Any questions on the setup for the problem? Okay. All right, so let's get to it. Okay. So first, we're going to start with our element stiffness matrices. Okay, so we'll start with element A. Okay. Let's start by stating the angle for element A. So the angle for element A, we can see it's a vertical element, okay, with node 1 on the bottom. And so in order to get into that orientation with node 1 as kind of the origin or the apex, we have to rotate up by 90 degrees, right? So this angle right here, theta 1, is 90 degrees. All right, so that tells us that cosine of the angle is going to be 0, and sine of the angle S is going to be 1, okay? Okay. So for the frame element stiffness matrix, there are a lot of entries here that involve, ratios of either the Young's modulus and the length of the moment of inertia. Okay. So actually what I find useful, and actually don't forget we have an E over L in front, right? So actually what I find useful is to kind of pre-multiply a lot of these factors so you can just plug them into the matrix. Okay, so the first factor we're going to compute here is E over L. That's the first. That's our coefficient out in front of the matrix. Okay, so we're going to take our Young's modulus. Our Young's modulus here is 30 times 10 to the 6 psi divided by the length. Okay, the length is given in feet, but everything else here is in inches, and so we convert this feet to inches. Okay, so we're going to have 30 times 10 to the 6 psi divided by 120 inches. Okay, this is going to give us 250,000 pound per inch cubed. Okay. Next factor that we have in our matrix is going to be 12i over L cubed, or L squared, excuse me. Okay. So you see that factor show up quite a bit in the matrix. So let's go ahead and just multiply it here and just plug in whenever you see it. All right, and so if we take those values for this element here, 12 times I for this element is 200 inches to the fourth, divided by L squared, we get 0.167 inch square. Okay. The other factor that shows up quite a bit is 6i over L. Okay. So once again, we're just going to plug in for this, and what we get is 10 inches cubed. Okay. All right, so now that we've done this, we can just plug all of these in. Okay. we do that, we do 250,000 out in front. All right, so a lot of this is going to cancel because everything that involves cosine is just going to go to 0. Okay. So we can end up with 1.67, 0, minus 10, minus 0.167, 0, minus 10. Okay. Just like we usually do, I'm going to take that first row and write it into our first column. And so our first column is going to be 0, minus 10, 0, minus 0.167, 0, and minus 10. Okay. All right, let's start on our second row. So our second row is 10, 0, 0, minus 10, 0. Okay, it's pretty simple on this end. I'm going to take that row and write it into the remaining entries in the second column. Okay. Third row, we have 800, 10, 0, 400. Okay. Same thing here. I'm going to take the extra entries in the third row and just write it into the third column. Okay. Next row, we have a 0.167, 0, and 10. Okay. Second to last row, we have 10 and 0. And our very last entry down here is 800. All right, and then we're going to write in the degrees of freedom here. So d1x, d1y, theta 1, d2x, d2y, theta 2. All right, any questions on this so far? So it's just plug and chug. It's just plug and chug, on super omega hyper plug and chug. So okay, so let's go ahead and move on. So let's go ahead and move on to element B. Okay. Element B is our horizontal element that's on the top of the structure. Okay. So for element B, let's go ahead and write out the angle. Okay, element B, our angle here is 0 degrees. Okay, because it's a horizontal element. And so based on that, we know cosine of the angle is 1, sine of the angle is 0. Okay. And once again, before we start plugging things in, let's pre-multiply some factors just so it's easy for us to kind of plug it in. Okay. So we have E over L. This is the same as the previous element, so that's 250,000. Okay. We have 12I over L squared. Okay. This is 0.0835 inch square. Okay. Then we have 6I over L. This is equal to 5 inch cubed. Okay. Okay. Let's go ahead and start writing the matrix. And so the matrix here, we start 250,000. So these entries are going to look a little bit different than the previous one because remember, cosine is active this time and not sine. So that changes kind of which terms are active in which areas of the matrix. Okay. All right, so for this first row, we have a 10, and then 0, 0, minus 10, 0, 0. Okay. So I'm going to write this into the first column. So we have 0, 0, minus 10, 0, 0. Okay. Second row, we have 0.0835. 5 minus 0.0835. Oops, we're at 0. There's a 0 under here. 0.0835 and then 5. Okay. Let's write that into the columns. We have 5, 0 minus 0.0835 and then 5. Okay. Next row is 400. 0 minus 5, 200. Okay. Same thing. I'm going to write those into the third column. Next row is pretty simple. We just have 10, 0, 0. And so we're going to write 0, 0 into the fourth column. Okay. Second to last row, we have 0.0835, then minus 5. So that minus 5 goes into the fifth column. And then our last entry here is a positive 400. D2x, D2y, theta 2, D3x, and theta 3. Okay. All right. Okay, so trudging right along. Let's jump to element C here. Okay. Let's go back to the figure here to determine what the angle for element C is. Okay. So element C is that vertical element on the right, and so it's going to bear a lot of similarities to element A. Okay. But notice how the lower number node here is up top, right? So the lower number node is 3 in this case, and it's at the top of the element. Okay. If we were to draw the positive x-axis originating from that node 3, okay, in order to get this element into the orientation that it's in, we have to rotate not by 90 degrees, but by 270 degrees, okay? So that's going to change the sign of our sine term, right? So instead of a positive 1, sine of 270 is going to be minus 1, okay? All right, so for element C here, we have theta is equal to 270. Okay. So that means cosine of the angle is still thankfully 0. And then sine of the angle is going to equal to minus 1. Okay. All right, so just like we did before, let's pre-multiply a lot of these factors so we can just plug it in. Okay. We have E over L. E over L is 250,000 pound per inch cubed. Okay. We have 12I over L squared. This is 0.167 inches square. And 6I over L. 6I over L is 10 inches cubed. Okay. All right. So our element stiffness matrix, let's just go ahead and plug all of these in. We have our E over L factor in front, that's 250,000. Okay. Then the entries in the matrix, we have 0.167, 0, 10, minus 0.167, 0, 10. Okay. Let's write those entries into the first column. So we have 0, 10, minus 0.167, 0, 10. Okay. All right, next row, we have a 10, 0, 0, minus 10, 0. Okay. Okay. Next row, we have 800, minus 10, 0, and then 400. Next row, 0.167. 0 minus 10. Second to last row, we just have a 10 and 0. So that puts a 0 down there. And then our last entry here is 800. All right. And so the degrees of freedom here connected to nodes 3 and 4. So you have D3x, D3y, theta 3, D4x, D4y, theta 4. All right. So just writing the element stiffness matrices for these is a doozy, right? And even though, you may talk about it and say like a standard beam by itself is a 4x4 element stiffness matrix, a 2D truss is 4x4. A 4x4 element stiffness matrix is only 16 entries you have to write down, right? Upgrading to a 6x6 is 36 entries. And so it grows literally exponentially. And so, definitely don't underestimate these problems and take them slow because they can definitely take a lot to do. All right, any questions on this? Okay. All right, so the next steps is of course assembly. And so we're going to assemble all of this into the same global stiffness system. I'm going to go ahead and combine that with the next step. And so I'm going to combine that together with boundary conditions as well, okay, just for the sake of time. And so our boundary conditions in this case are pretty straightforward. We just have fixed supports on nodes 1 and 4. So that's going to cancel out those rows entirely. And then for the other ones, we have just two simple nodes. Okay, so I'm going to start with the matrix here. So the matrix here, you have 250,000. Okay. All right, and so we have 4 nodes. Each node has 3 degrees of freedom. So that means our global stiffness system here is going to be 12 by 12. Right? So let me go ahead and write in all the columns here. So we have D1x, D1y, theta1, D2x, D2y, theta 2, D3x, D3y, theta 3, D4x, D3y, theta 4. Okay. So I'm going to scroll to the right here, but just don't forget that 250,000 down in the front. Okay, it's very easy to forget that. All right, and then for the rows, we have D1x, D1y, theta 1, D2x, D2y, theta 2, D3x, D3y, theta 3, D4x, D4y, theta 4. Okay. The forcing vector is there as well. It's just we'll deal with it later. Okay. So first thing, since we know where the fixed boundary conditions are, let's just go ahead and write that in directly here. Okay. We know we have fixed boundary conditions on node 1, so that's all 3 degrees of freedom for node 1. Okay, so that's going to be 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. All right, so since we know already that the first three rows are going to be basically canceled out because of the boundary condition. So let's just save ourselves some trouble and just put that in. Okay. Same thing for the last three rows because node 4 is also fixed. Okay. Let me go ahead and put that in. So 1. Much harder to see from down here. 2. Oh, I'm sorry. The 1 should be on the third to last. That one. Okay. 0, 1, 0, 0. We have our fixed support boundary conditions in, and that's half the matrix, honestly. So we've already kind of done a lot of the legwork here. Okay. Okay, so now let's go ahead and insert our other element stiffness matrices. Okay. So let's start with element A. So I'm going to use my coloring scheme here. We know element A is connected to nodes 1 and 2. So let's go ahead and highlight that area of the matrix here. Okay. So that's all 3 degrees of freedom for node 1, all 3 degrees of freedom for node 2. Okay. We're gonna have a box just like that. Next, we have element B. So element B is nodes 2 and 3. Okay. So that's everything with node 2, everything with node 3. Okay, with all of these columns here. Okay. Element C here is nodes 3 and 4. That's all of these guys right here. All right. So of course we have some entries here that aren't boxed, that aren't included in the element stiffness matrix. So we can just go ahead and put zeros for those. Okay. We have 0, 0, 0, 0, 0, 0, 0, 0. Okay. And then everything else in here is going to be just copying the entries over from the element stiffness matrix. Okay. All right. So let's go ahead and write that in. So we have a minus 0.167, 0, 10. I'm gonna do the non-overlap parts first. 0, minus 10, 0, minus 10, 0, 400. Okay. So those are all the non-boundary condition, non-overlap parts of element A. Okay. Now let's do the overlap parts. Okay, so we have the overlap between element A and B. So this is going to be 10.167, 0, 10, 0, 10.0835, 5, and then 10, 5, 1200. All right, so that's all of element A. Let's go ahead and fill in for element B now. So for element B, we have, I'm going to start in the top right coordinates. We have minus 10, 0, 0, 0, minus 0.0835, 5, 10, minus 5, sorry, 0, minus 5, and then 200. Okay. And then the bottom left, actually the mirror image of it, so we have -10, 0, 0, 0, minus 0.0835, -5, 0, 5, 200. Okay. All right, next we have another overlap portion. So this is now the overlap portion between elements B and C. Okay. So this is a 10.167, 0, 10, 0, 10.0835, -5, 10, -5, 1200. Okay. All right, and then the last portion of the green here, the top right of the element stiffness matrix for element C. This is a minus 0.167, 0, 10, 0, -10, 0, -10, 0, 100. All right. Miraculously, things actually stayed kind of relatively lined up for a 12 by 12 matrix. All right. I know this is torture. It's torture for me too, but it's but we need it. We need it to set up the next part of the class. All right, any questions on how we did that assembly there? Okay. All right, so the last part here is our forcing vector. Okay. So that's where our loads are going to be applied. Right, so thankfully this is pretty simple. So this is all equal to a 12 by 1 vector here. Okay. So remember, we have two loads here. We have a load that is applied on node 2 in the x direction. Okay. So for the first node here, we have 3 zeros just because that is a fixed boundary condition. For node 2, we have a 10,000. Okay. To represent the 10,000 pound load that's being applied on node 2. Then we have 2 more zeros. Okay. Node 3, we have a counterclockwise moment of 5,000 pound inches. And so we're going to apply that on the theta 3 row. So this can be 5,000 here. Okay. And then node 4 is just going to be all 0. So 0, 0, 0. Okay. All right. So now that we have our assembled global stiffness system, we've incorporated all the boundary conditions. Our forcing vector is all filled in. Okay. Now all that's left to do is to solve the system. So you would plug this in to MATLAB. And so if you solve the system, you get the following results here. We have d1x, d1y, and theta 1. Okay. All these are equal to 0 because of the fixed support. Same thing for d4x, d4y, theta 4. Okay. All these are equal to 0 because of the fixed constraint. Okay, traditionally boundary condition. All right, next we have the deformations at node 2. So d2x is going to be 0.211 inches. d2y is 0.00148 inches. And theta 2 is minus 0.00153 radians. Okay. And then we have the deformations at node 3. So we have d3x, d3y, theta 3. D3x here is 0.209 inches. D3y here is minus 0.00148 inches. And theta 3 here is a minus 0.00149 radians. And that is our solution to a very simple structure, but with lots and lots of writing and lots of matrices and vectors. Okay. All right, any final questions on this? Technically, you can. And so you'd basically set it up in the exact same way. So you would take your deformation solution, you'd multiply it by the elements, the global stiffness system that you did before the boundary conditions. And so actually, you know, this matrix wouldn't be viable. You'd have to kind of replug in the element A and C that we kind of already replaced with the Dirichlet boundary condition. But you definitely can get the reaction forces here. Mhm. All right, any other questions on this? Okay, all right, so that's all we got for today. And so when we come back on Tuesday, we'll finish up these notes. I just have one more example to do. And then we'll start coding stuff in MATLAB. All right, so thank you guys for coming this week. Hope you guys enjoy the rest of your day. Hope you guys have a good weekend, and I will see you guys next week.
Yeah. I don't know.
Thanks, everybody.
Well, there was that moment on the other side, right? So.
Okay, guys, have a good weekend.
Professor?
Yeah.
So the node goes for 2 goes to the right.
Yes.
0.21 and up 0.14.
It goes slightly up, and so it's you can see the magnitude for D2Y there is like 2 orders of magnitude less than the other one, so it's very slight. And so basically you're not going to get any upward movement from the force. So all the upward movement is going to be from the from this moment right here, or a combination of the moment and this one. So basically what's happening is because this is kind of pushing in this way. So the force here is pushing in this way. There we go. We have a little bit of support here from element A, right? And so because this is kind of pushing this end down like this, and so this is going to kind of, it kind of like tilts it kind of like that. That's kind of an extreme version of that. And so what you have kind of is like a, actually node 2 has a negative deformation. Or node 3. Yeah, that makes sense. So hang on. So through this kind of rotation right here, it's going to kind of bend downwards. My brain's it's a combination of kind of like, you know, you have kind of this supports here from these kind of frame elements here, which are these frame elements here are basically acting like trusses at this point. In terms of supporting that that rotation. And so what the heck am I saying? I don't even know what I'm saying. It could, so I think what may have happened here. So even though, you know, this system, we were able to solve it, but in reality, this system is still very close to singular, because you can see this matrix is still very close to being symmetric, right? And so if you kind of look on both sides, so these results right here for the D2X, even for the thetas, I would say are mostly, you know, you're getting kind of close to kind of numerical error in those just because the matrix is pretty close. I think if you compute the condition number, that matrix is going to be very close to 0. And so, yeah, I'll think about it a bit more. I'll have a better answer for you on Tuesday, but I wouldn't put too much stock into this just because it's so much less than the other ones, than the X deformations. Yeah. Mhm.
Like catching up from last Tuesday.
Oh, I see.
Yeah,
I see.
doing the ANSYS stuff too.
Ah, I see. Yeah, ANSYS was yeah,
See,
we've
there
been pretty
doesn't
busy.
zip to be.
I think I did.
Yeah.
This archive thing.
Yeah.
Yeah, ANSYS has got to figure that out. It's really annoying to move projects between computers, but But most people use Ansys on a workstation at work, and so they just work on the same workstation all the time anyway, so. I guess it's not too much of a request.
Did you finish your hot dogs?
I did.
Oh.
Felt, I still kind of feel awful. My poops have not been very pleasant at all this week.
Wait, so how many did you eat total?
I had like several packages, I want to say like almost 30.
Wow.
Over the course of like almost 10 days.
Oh,
That's gonna mean like 2 hot dogs per meal, yeah. There were different kinds of hot dogs, so I had hot links, I had chicken hot dogs, I had just regular hot dogs, and so I had at least some variety that way, but yeah, not healthy at all. Happy to be done, happy to, sleep good, poop good, and feel good after this.
And there's people, the competitive people.
I know,
It's crazy.
That's what my friends are like, oh, you're like Kobe Island. No, I don't want to, that is not a career I want to go down.
Yeah, I think they just throw it up.
Yeah.
I don't know.
They have to, there's no way their body can process all that.
You can go, I'm just sending the file to myself. Yeah. Bye.
All right, see you guys.
I'm just uploading my file.
No worries, take your time.
It's the zip file that
Yes,
okay.
it's like the extension is WBPZ.
PC, right?
Yeah.
Okay.